All right, good morning. Got exams back for you. I'm going to pass them out and then we'll start talking about them. So just take a minute and please be patient with me as I don't quite have everyone's name mastered yet and I'm not great with Louisiana. Feel free to correct me if I get something weird. Micah Law? Colin Hedges? Madeline? Isabella Preston? Emily Agno? Derek LeBlanc? Madison Ford? Emma Champagne? Charles Barros? Aiden O'Neill? Leighton Draw? Luke LeBlanc? Cameron McKinsey? Joshua Levine? Darby Fricky? Michael Taylor? David Peterson? Okay, so plan for today is really just to go through this, answer any questions you have, kind of make sure we're understanding what was good and what went wrong. As you can see here, the average was a 77. Bit of a distribution, only 2 A's, so that 100 category doesn't mean that was 100. That was anywhere between above 89 and 100 or below, right? So there's a couple A's, so not too many. I think that overall, some of the questions were a little trickier, or there was maybe just a lot of small places where it was a little tricky. But I think you did all right for the most part. Just a quick recap on how I give partial credit. What I'm usually looking for, well, first of all, check to see if you have just the right answer. That's great if you do. And if you don't, what I'm looking for is to see that you're on the right track in terms of getting the core concepts correct. If it was just you missed it by 1 decimal place, that's a pretty small error. You just made a decimal place change at some point or missed a unit conversion just by a tiny bit. That'll probably just be one point off. If it's, you were doing a mass balance and it was supposed to be a batch, but you were doing a CSTR, that kind of mistake, it's more like 25 to 30% off, and it's just sort of off of that component of it. So, for example, problem 1, I've got split into three portions, right? So each of them are worth about 8 points to total the 25. I guess 988 or something. And so if you were to do a kind of a conceptual mistake on one of those, like part A or something, that'd be like 2 to 3 points off, sort of a thing. And then if it's like multiple big mistakes like that, you'll see that there's more points off. And if you just kind of gave it a shot, or maybe you wrote a few things down, maybe you'll get just a bit of credit. So I guess if you didn't really give it a shot, you won't get much points. If you did give it a shot, even though you're way off, you'd probably get at least a portion of the credit. All right. Okay, so with that, we'll we'll go ahead and get into it. Any questions, concerns? I posted the grades last night, so you should have seen that already, or may have seen that already, to Moodle. Okay, so problem 1 was a bit tricky. It really was just a mass balance problem in the context of some chemistry. So it says, we have a report that says hydrolysis of iron can be modeled with a first order rate equation. We have the rate is equal to negative Kc for that. In a batch experiment at pH 3.65, 20% of the initial iron is hydrolyzed after 25 seconds. Now, here's the first tricky part. That means 20% was removed or changed, right? We're not saying we have 20% remaining, so this is 20%, we'll call it transformed after 25 seconds. We assume that the reaction will act as a forward reaction, and then the part A says, how long will it take before 99% of the iron has been hydrolyzed by the batch system? So in this case, really this is a lot like solving a half-life problem, and what we're really after is simply finding the K first of all for this reaction. We're given enough information to do that, and then applying that to a batch scenario and then solving for the amount of time it would take for that 99%. So we need to find K. We are given some information on what it looks like if the final over the initial has reached, let's say, if we're doing 100 parts total, 20 parts are gone. That's going to leave us with 80 parts over 100 in 25 seconds, right? So that would be the way to look at that. So we could say, in terms of our mass balance, we know that in a batch system, we ultimately end up, we could start like this, V dc dt. I'm going to write it C over C naught. If we start with V dc dt equals negative V kc, that will ultimately integrate to give us the natural log of C over C naught equals minus KT. So we've done that a bunch of times now. So if we insert it here, we can say the natural log of this 0.8, which is coming from there, would be equal to negative K, which we need to solve for, times 25 seconds. When we then solve for K, so divide the natural log of 0.8 by negative 25, K should come out to be 0.00893 per second. So from there, then we can continue on with the problem. So at that point we say, well, how long will it take if we know that K? We'll say the natural log of 0.01 remaining, 99 removed, should be equal to negative K times the time, and we're solving for the time. So we put that in, and we should be able to get 516 seconds. Okay, so a fair amount of you got that. I think there's a couple people that solved it as if it was 20% remaining, and that certainly would be a little bit of a trick. What's the name? That's it. There we go. Okay, so then from here we're asked what is the resonance time required to achieve that same 99% if we used a CSTR at steady state. And so really we're just using the K again here, and so rather than penalize you again if you had not solved for K properly, what I was really looking for is to see you set up a mass balance here. So what I was wanting to see regardless was something, something where I could tell you were thinking about it in terms of what's happening here with some reaction, such that steady state we'd have what's going in minus what's going out minus that reaction because it's a decay. So in that case, you need to solve this for C over C naught, and then ultimately solving that for the residence time. So you can do it a few different ways algebraically. We could start off by saying, well, we know we've done this a bunch of times, and that's going to be 1 over 1 plus theta k if you wanted to, but we have to solve for the theta. So another way you could do it is simply say, all right, well, let's go ahead and divide everything by q. Minus theta, v over q is theta. Go ahead and add the c terms to the left. So c plus theta kc. And then you're just really working on isolating theta while also getting it in terms of some ratio of c and c naught. And the reason that is so helpful is because if you get it in a ratio like that, then you have a situation where you can apply the 99%. So we want to keep that in mind. So rather than solving for, theta with some sort of like c naught minus c, blah, 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 it's just nicer if you can go ahead and get it directly into some version of c over c naught or some ratio there. So I'll just divide both sides by c then. So 1 plus theta k equals c naught over c. And we can go from there to say theta should be equal to this c naught over c minus 1 divided by k. All right. So any way you go, and what you could say here as well, if c over c naught is 99, then that means the initial concentration is 100 times what you started with. So you could literally just write 100 minus 1 is 99. So 99 divided by k is kind of what your equation says. At any rate, theta will then, for our answer, be 11,092 seconds. Or you could write it as 184 minutes. 185 minutes. Okay. All right. So far so good. All right, part C said, what is the residence time for the required if we had two identical CSTRs to achieve this hydrolysis? Same 99%. So instead of going through the one reactor with 1 theta, what we needed was flow going from one into the next, and they're identical. And we want to know what the C final is. We'll call it C2. This would be C1 and C naught. Same Q is going to be going through all of them. They're identical, so we could say, now this says total residence time. So there's a potential caveat here. We could get ourselves in trouble if we're not careful. But we could call this theta 1 and theta 2 and say theta 1 is equal to theta 2. So that will be 1/2 of the theta total. So that means the volumes are equal, all of that. So we can then think about this in terms of, okay, we need to have some final concentration compared to what we started with equal to that 0.01. So 1% remaining is our threshold. So in order to solve a system where we can achieve this C2 over C initial, here's where we could take a look at it in terms of multiplying the mass balance of what happens in one times what happens in the other. Because to get to C2 over C0, we can take C1 over C0, which is just solving the mass balance in one of those, and we multiply it by the mass balance solution for the C2 over C1, right? So we use the fractions there like that. So for either of these cases, if we solve for C1 over C0 or the other way, we can derive an equation like we just did a moment ago, right? And that would be 1 over 1 plus theta k. Now this is theta for one of the reactors, right? I'll go ahead and just label it theta 1. So if we take and say also that C2 over C1 is also 1 over 1 plus theta, I'll label that as 2. We know these are equal thetas. So these are our two values. So if we want to find C2 over C0, that's simply 1 over 1 plus theta k times 1 over 1 plus theta k, right? We could write that as 1 over 1 plus theta k quantity squared because the thetas are equal. So that's the approach I took. I said C2 over C0 would be 1 over 1 plus theta k, just square the whole thing. And then to solve, we also know, by the way, this is equal to 0.01. So to solve that, I took it and said, well, square root of 0.01 would be equal to 1 over 1 plus theta k. Multiply both sides by 1 plus theta k, divide both sides by 0.01. That'll give us 1 over square root of 0.01. And we can see here, to solve for our theta, we just need to rearrange just a little bit further. And running out of room a little bit, but theta should be equal to, did I do that? I did something backwards, didn't I? No, okay. 1 over square root of 0.01 minus 1 and all that divided by k. And when we solve for it, theta ultimately we can find equal to 1008 seconds or 16.8 minutes. Okay, and again, if you didn't get the right k, what I was looking for is for you to take this this type of an approach, multiplying these two fractions together to find a solution. Now, what I just wrote here, I'm actually second guessing myself a little bit. This should be the theta for 1. So the theta total actually should be double that, and I'm not sure if I calculated that. Does anybody have this answer or the Can somebody check this math to take, well, I guess I'll check it in a second, but I just want to see if I doubled that or not for it. Yeah, so I didn't, I clarified the question after I wrote it and then forgot to solve. So it should be double that. So this would be theta 1. So if I marked you incorrect for if you had double this, please let me know, since I asked for something else and I graded you for this. if I gave you full credit for this, count yourself as lucky because I made the same mistake. So theta total should be 2016 approximately seconds, or what was it? 33.6 minutes. Okay. I know that some of you got the 1,008 seconds. So bring your exam to me after class if I counted you wrong when you had it righter than I did. Righter, more correct, something. Okay. So problem 2, we had a coagulation flocculation type of problem. Part A was really looking at the mixing intensity. So we have a system where we have jar tests being used to test coagulation. We've got a 10-liter jar submersed with a submersed stirrer for our questions. So some jar, typically it'll look something like that, stirring away. You say the water is 20 degrees Celsius, so we can, without even looking at the question yet really, we can go ahead and write this down from our lookup table. We are given then, so part A, if the stirrer is powered by a motor that's supplying 5 milliwatts, what is the mixing intensity of the water in the jar? So power then is going to be, we need it in watts, but we're given it in milliwatts, so we'll go ahead and convert that. It should be 0.005 watts. So milli is 1,000th of, so make sure that conversion happens correctly. Then the mu, that's our dynamic viscosity of water, already have that written. And then the volume we are given in liters, but to match our units here, meters, we need to put it into cubic meters. So we were given 10 liters. We know there's 1,000 liters per cubic meter. So this should be 0.01 cubic meters. Okay, so then we are ready to solve our equation for G, square root of the power divided by dynamic viscosity divided times the basin, the volume of the basin. So when we do that, we should find G is equal to 22.34 per second. All right, so chances are if you missed that, it was some issue with not noticing or converting the units properly, but pretty straightforward otherwise. So part B has kind of three answers I was looking for to kind of gauge where you got to with this. So it says if there are initially 1.5 times 10 to the 7th particles in the jar, all particles are 40 micrometers in diameter, what is the average number of singlet particles in aggregate after 30 minutes? That's asking, what is this? N not being the singlet ones that we started with, and N being the final ones that we end with, or the number of them. Okay, so then it says assume the particles are completely destabilized, and I ask you to highlight these pieces along the way. All right, so first of all, and we can kind of use this as a guide, we need this omega term. Really, to solve our problem, we need a mass balance, right? So we could actually start there for a moment. Say, in a batch system, we can treat it like this. We have a decreasing number of particles, so it's going to be a negative reaction with some k that we need to solve for, times that number to the 1 power in that volume. So we can, as usual, translate this to the natural log of n over n naught equals negative kt. That'll integrate. And from here, we actually kind of would probably need to rearrange a little bit, right? So let's go ahead and say this is n over n naught equals e to the minus kt. And we actually need n naught over n, so we can flip it. N naught over n equals 1 over e to the minus kt. Okay, so that'll give us our mass balance component. We know the time, we were given 30 minutes, and now we just have to find the k, right? So we know k has some dependency on the collision efficiency times 4 times our flock volume times our mixing intensity that we solved for, all that divided by pi, which means we need our omega, the flock volume, which is the volume of a sphere of the initial particles times how many particles we have per volume. So this will be the diameter of the particle cubed times pi times n naught, all divided by 6. Okay, so most of you did pretty well to get this flock volume. K required the correct G. So one thing to note here is what I was looking for. First, for the omega, did you do that correctly? And most of you either did it correctly or missed a bit of a unit conversion, but yeah, I could tell you did it for the most part correctly. Then K, if you didn't have the correct G, it was certainly going to be off. But again, I could take a look to see, if that was the holdup there, or if it was omega or what. So, all right. So the flock volume, we'll go ahead with that. We know that n naught is 1.5 times 10 to the 7 particles, but that's in the jar. So that's divided by 10 liters, which, again, we need to convert that to cubic meters if we're going to properly insert it into this equation that is in meters. So we can rewrite that to say this is going to be 1.5 times 10 to the 11th particles, I'll just say number of them per cubic meter. So that's accounting for the 10 down there and also for the conversion to cubic meters. Okay, so that gives us our n naught, so that would be one's potential source of error there. Diameter of the particle would be 40 times 10 to the minus 6 meters. So once we put all that in, the omega should come out to be 5.03 times 10 to the minus 5th. And that's a unitless value, right? It's volume per volume if we've done our conversions correctly. The units should cancel. So then at this point, we should have everything for K to solve it, and then we can insert that here to find our last value. So for our collision efficiency, we were told that they are completely destabilized, so that means this should be 1. And we have everything else. So if you had these numbers in place, it should have come out to be 1.43 times 10 to the minus 3 per second. And again, my aim was to not take off very many points here if I could tell this was just coming from an error prior to that. So then the last component was to solve n naught over n, and this type of a derivation is what I was looking for. So
n naught be 1.5 times 10 to the 9?
The which one?
Yeah.
N naught? Maybe. Let's take a look.
You're dividing by 10, so that's 10 to the 6 times 10 to the 3rd, so that's 10 to the 9th.
You know what I did wrong here? Is that? Yeah. Let's see. That sounds correct. 10 liters, and this was that many liters in the jar. I think you're correct. Let me see if I just have a problem in my Excel solutions. Yeah, that's actually the value I wrote in my Excel solutions with 10 to the 9th. So sorry. Okay, now the question then becomes, does that affect the next problems, or was I just copied over something incorrectly? With that value, I think I'm still getting the same values otherwise. So I think I just wrote it wrong. Does that sound correct? Okay, good. All right, so if I had just simply calculated it all wrong and used the wrong calculation here, this guy would have changed for sure, which would have then changed everything else, right? So fortunately, that was just me making a mistake when I was copying it over to my notes here. Good catch, and you're exactly right, because that would be 6, and then plus 3 is 9. Okay, so this should still be the k, and then if you put all this in the n naught over n with these values, should be 13.11. All right, does that make sense? Okay, so part C, I think there were 2 of you that made it through this entire problem and got all of it correct, so congratulations to you too. For this part of the problem, by now there was so many spots to make a mistake. I wasn't actually expecting so much to have the exact right answer. What I was really looking for is for you to follow a pathway that could get you there, right? If you did have the other answers. So from here, it says, all right, what would the sedimentation velocity be for the resulting aggregates after this 30 minutes? So we just solved for that 30-minute run, and we're given some particle density. So rho p, this is 1.33 grams per milliliter. We can get the density of the water from our lookup table under these conditions. And we know that we're going to have to solve this velocity equation. That'll be g times rho particle minus rho water times diameter particle squared divided by 18 times mu. Okay, so that'll be kind of the overall process there for the velocity, but the diameter of the particle, we actually need to focus in on that. That's going to be the diameter of an aggregate, not the particle itself. So we were given some information about the diameter of the particle. That was 40 micrometers. But the diameter of the aggregate, we don't know yet, so we have to solve for that. And that's where we use the answer to part B. So really what I was looking for is that you were recognizing that we need to do some conversion, given that we just made them to be bigger particles. That's that 30 minutes that we let it run. So now we have some indication that the volume of the aggregates we know should be 13.11, or really what I'll just do here is just write your answer to n naught over n times the volume of one particle, right? And so if you did anything that resembled that to get a new diameter, to not just use the 40 micrometer diameter, that's what I was looking for. And so this was the process, and we did a problem like this in class, so we could ultimately find the diameter. It should be the cubed root of this n naught over n. In our case, that was 13.11 times the diameter of the particle cubed. It's because if you take the volume of a sphere and the volume of a sphere, the pi's will cancel, the divided by 6's will cancel, and you're just left with the diameter comparison, including that conversion ratio from the volume. Okay, so then using the 13.0, or excuse me, 13.1, that should give us a diameter here equal to 9.43 times 10 to the minus 5th meters. And then we put that into our equation up here. Put all that in, and we should get a velocity term of 1.61 times 10 to the minus 3rd meters per second. All right. So hopefully what you'll see is if you just inserted this straight away, that was probably I think 3 points off. And then I would have recognized, if that's all you did, this problem is the same for anybody. And so then you should get a particular number times 10 to the minus 4th. It was like 2.8 or something like that. And that's the incorrect answer, but I could tell that you got the units correct if you got that particular answer. So if you were also making some unit mistakes along the way, I might have taken off an extra point or something. All right. You're good on that? All right, so problem 3. We have a granular media filter with a loading rate 7.5 meters per hour, dimensions of 10 meters by 6.5 meters, and an effective filtration rate of 7.15 meters per hour. A complete filter cycle is 78 hours and includes 1 hour of downtime for rinsing, backwashing, and maintenance. So it's 1 hour blocked for all that stuff. So part A says, what flow rate does an individual filter produce during production? Okay, so this really makes you think about what really we're talking about, right? We have our filter. That would be like 10 by 6.5. And when we're saying during filtration, clearly not drawn to scale, that's talking about when we're adding water to it, when we're actively loading water. So if you recall our filtration cycle, right? We have all the backwash stuff, a bit of rinse, but mostly it's filtration. And what we know about what's happening during filtration is that's our loading rate. We're loading water at some rate. So when we ask about a flow rate, we need a Q during filtration, during that production phase. That filtration, we could also call that production. Okay, so what we're looking at is this is going to be VA times the area of the filter, or that, yeah, because that's going to be effectively meters per second, or meters per, I guess, hour, times square meters, right? So this will going to simply be 7.5 meters per hour times 65 square meters. And that should give an answer of 0.135 cubic meters per hour. Now, sorry, per second. It asked it for the answer in seconds per seconds. So we'll have to convert, this is times 3,600 seconds per hour. Okay, but that should, divide by that. Divide by 1 hour per 3,600 seconds. There we go. Okay, so that should give us our answer there. If you did leave it in cubic meters per hour, it would have been, I think, 486 cubic meters per hour. Okay, so the tricky part here, I suppose, was recognizing specifically what we're talking about. We were not using the effective loading filtration rate. We were using like what's happening in that moment, right? And so just understanding what it was asking for there.
Yeah, that confused me because it says what does the individual filter produce? So to me, produce means what is your final result?
Right, right. Yeah, sorry about that that confusion there. I suppose if I could probably reword that to say what flow rate does an individual filter achieve, maybe, or what is the flow rate through one filter during production. Okay. All right. Okay. So part B says how many filters does the plant require if it must treat a total flow rate of 1 cubic meter per second. So here, really, we're looking for some Q total for the entire plant. That's the 1.0 cubic meters per second. In reference to this a moment ago, we might say to ourselves, oh, it should be somewhere probably a little bit less than 10, because one filter, when it's like providing the full flow, is, a little over 1/10 of what we require. So just mentally, we could say, all right, something near 10. But we need to know kind of the effective flow rate provided by each filter, and that's when we'd use the effective loading rate. So Q, I'll say effective for one filter, if we want to write it that way. That value we could write as R effective times the area of the filter, which is probably what several of you solved for here. And so if you had then just took that and put it straight into here, you'd be just fine. And I think a lot of you did that. So then we can get to a final number of filters if we simply write it and say, okay, well, number of filters required would be the total filtration needed divided by the flow rate provided by just that one filter, over the course of the total cycle, or the effective, however you want to write it. So when we do that, the number of filters required should come out to be 7.75, which we have to round up to 8 filters. That would be our answer. All right, so part C was, again, another one that was a bit tricky. So it asks us, what is the volume of water needed for backwashing plus rinsing for the filter in each cycle? Now, it's tricky because we weren't actually given the times. We weren't given the time for the backwash. We weren't given the time for the rinse. We weren't given any information about, well, is there an air purge? And we don't know if there's some sort of backwashing loading rate. Now, maybe we can make some assumptions there, but what we are given is an effective loading rate. We know that, and we also know that the equation for that might be handy, because this is the volume filtered minus the volume backwashed minus the volume rinsed, divided by the area of the filter times time of the total cycle. Well, another thing we were given was the time for the filtration. That was all but 1 hour, right? So that would be 77 hours, I think. It was a total of 78 hours. Yeah, 1 hour was for all the other stuff. So one thing we could notice here is we can rewrite this to say this effective loading rate is equal to this volume filtered minus the sum of the volume backwashed plus the volume rinsed. And then hopefully what you see here is we've just identified the thing we need to solve for, which is right here, these brackets, right? So then we have a way to find it, even though the problem, didn't quite give us a straightforward way. So we can rewrite this and say this volume filtered. I'm just going to multiply the AFTC from both sides, minus this thing we're after equals R effective times area of the filter times total cycle time. So I guess we could now add this. Could just add and subtract the other way, but so we'll go ahead and add this to the other side and subtract that over. So our VB plus VR is going to be equal to VF minus this stuff, R effective times area of the filter times total cycle time. So really this is the volume filtered minus everything that was, it's kind of like that difference, right? That what we actually filtered times the volume, minus that volume that we effectively produced. So that's REF times the area times total cycle time. So when we put all that in, we have each of these parameters. We should find that this is 1,287 cubic meters. All right, and I saw several of you trying different ways algebraically to kind of get there, recognizing that there was probably something to do there. So I've thought a lot of you were on a good train of thought there, even if you didn't get it. Okay, so problem 4, we had a membrane module consisting of several tubular membranes, effective surface area of 12 square meters. The membrane system is operated in cross flow under constant flux to yield 1,500 liters per hour of water. It's 20 degrees Celsius. And part A says each tubular membrane is 2 meters long. Go ahead and draw something. Got 2 meters in length. We have 2.2 centimeter outer diameter. And the question is, how many tubes does each unit contain? So I'm going to go ahead and put this into meters here. So each module has a membrane surface area of 12 square meters. We're given this outer diameter, and I think it says, does it say? All right, it doesn't specify, but we can kind of assume that we're only given the outer diameter, so that's the diameter we kind of need to use. Given no information to get an inner diameter, so I think I meant to specify that we're going outside in, but we did, okay, good. All right, so definitely using the outer diameter. So now we just need to solve for the area of one tube and see how many tubes it requires to get there. So the area of one tube should be the area of a circle, or excuse me, the circumference of a circle times the length of the thing. So that should be 2 pi r is the circumference, or that would also be pi times the diameter, and then multiply by the length to send that across the whole tube. So the area of one tube should be, do I have it written? Maybe. Should be 0.138. Square meters. And so then we say 12 square meters divided by 0.138 square meters per tube should give us 86.8 or 87 tubes. Okay, makes sense? All right, so then part B says, if we have some membrane resistance at 7.85 times 10 to the 12th per meter, what is the operational pressure that must be applied across the membrane to achieve that flow of 1,500 liters per hour? Now, this flow rate here, we have to recognize that 1,500 liters per hour, that's a flow rate, and we need a flux to relate to the transmembrane pressure. We have this equation that relates our flux to transmembrane pressure and membrane resistance. So in order to get this, we have to take this 1,500. We also recognize that flux is some flow rate divided by some area, right? So we're going to need this 1,500 liters per hour and convert it into, well, first of all, divide it by the area of a module, which was 12 square meters, and then put that all into meters and seconds. So when we do that, we should get a flux that is equal to 3.47 times 10 to the minus 5th cubic meters per square meter per second. So just real quick, we'd have to multiply this by 1,000 liters, 1 cubic meter per 1,000 liters. To convert that, we'd also have to multiply by 1 hour per 3,600 seconds. Okay. So with that flux, then we can relate it to the TMP that we are trying to solve for. In fact, what I'll say is we can just simply say that TMP should be equal to the flux we just solved for times dynamic viscosity times that membrane resistance that was given. Okay, so chances are, if you missed this, perhaps you took the flow rate to be a flux, or didn't convert the units, or some combination. So this was the process when you solve this with those units correctly. That comes out to be 2.73 times 10 to the 5th pascals, or we can convert that to kilopascals as the answer requested, should be 273 kilopascals. Okay, so then last part C, says what pressure must be applied to keep the flux constant if the membrane fouling doubles the membrane resistance. So the only thing that happens here is our T, this nu, is going to be equal to 2 times that initial RT. So if we look at our equation, transmembrane pressure was equal to this flux times the mu. So really the only thing I did to grade this one was to see if you appropriately doubled the value here from what you had a moment ago. So some of you certainly got this problem wrong. And so if you had some number and down here you reported twice that number because it should really just be 2 times RT, then you'd be in good shape. So in that case, this should come out to be 546 kilopascals. All right. Any questions? Feel all right about it? A little bit tricky? All right, so We have a few minutes left, but I think I'll just call it a day for you here. So we'll resume talking about disinfection on Thursday.